electrical components, voltage and current are inextricably linked by Ohm's law. If you increase the voltage across a simple wire or resistor, the current scales linearly in response. But a diode breaks this linear relationship. When the voltage polarity is reversed, current ceases immediately, rendering the standard calculation irrelevant. This absolute rejection of proportional scaling makes the diode the foundational nonlinear component in modern electronics. It acts as a strict one-way valve, yet it contains no moving parts. Its ability to block electrical current is not a mechanical function, but the result of an engineered electrochemical boundary. To understand exactly how it dictates the flow of electricity, we have to look past the standard plastic casing and examine its internal atomic lattice. The mechanics of modern circuits, how they manipulate, isolate, and direct energy on a macro scale, are entirely dependent on the solid-state physics operating at this microscopic level. This diagram shows the starting baseline for a diode, a highly uniform lattice of pure silicon atoms. In this state, there are very few free electrons, making pure silicon a poor conductor. To change its electrical properties, we introduce specific impurities. By adding boron atoms to one side of the lattice, a process called p-type doping, we create localized electron deficiencies. These empty spaces are called holes, and they act as positively charged carriers within the crystal. On the opposite side of the lattice, we introduce phosphorus atoms. This is n-type doping. The phosphorus provides an excess of free, unbonded electrons, creating a surplus of negatively charged carriers. The critical mechanics of the diode are initiated the exact moment these two differently doped materials are merged to form a single junction. Because there is a high concentration of free electrons on the N side and a high concentration of empty holes on the P side, a process called diffusion begins immediately. Free electrons naturally migrate across the concentration gradient at the border to fill the empty holes on the other side. As these free electrons migrate, they leave their positively charged parent atoms behind. The holes that are filled leave behind negatively charged parent atoms. This creates a zone of fixed ion cores that are structurally locked into the crystal lattice and cannot move. This establishes a specific boundary zone completely devoid of free charge carriers. In solid-state physics, this is known as the depletion region. The presence of these fixed, oppositely charged ions creates a strong, localized electric field vector straight across the junction. We call this electrostatic barrier the built-in potential. For standard silicon devices, it averages approximately 0.7 volts. This built-in potential acts as a repulsive force that halts any further electron diffusion. There is no physical wall inside the component. This self-regulating 0.7 volt electric field is the primary mechanism governing directional current control across the junction. To make this junction useful in a circuit, we have to manipulate that built-in potential. We do this through biasing, which is simply the application of external voltage. First, we connect the positive terminal of a battery to the N-type silicon and the negative terminal to the P-type. This configuration is known as reverse bias. Because opposite charges attract, the external voltage pulls the free electrons and holes outward, away from the center boundary. This external polarity directly aligns with and reinforces the internal electric field. As a result, the internal depletion region stretches significantly wider. With the electrostatic barrier reinforced, current flow across the junction is restricted to a negligible microscopic leakage. To open the valve, we apply forward bias. This means reversing the battery connections so that positive voltage is applied directly to the P-type silicon. Now, the external voltage pushes the charge carriers toward the center, directly opposing the diode's internal built-in potential. But current does not flow immediately. The external voltage must rise until it exceeds that 0.7 volt threshold. The moment it tips past 0.7 volts, the central depletion region is overpowered and collapses entirely. With the barrier removed, drift current suddenly dominates. The junction floods with charge carriers, and electricity flows freely through the component. By strictly expanding or collapsing a microscopic electrostatic zone, the diode functions as an incredibly precise, voltage-controlled valve. We can translate this atomic physics into a current voltage, or IV, curve. This graph plots voltage along the x-axis and current on the y-axis, and it serves as the standard engineering tool used to predict diode behavior. When we map the physics of reverse bias onto the graph, the line extends horizontally along the negative x-axis. It remains virtually flat at 0 on the y-axis, showing that essentially no current passes. When we apply forward bias, the line travels along the positive x-axis until it hits the 0.7 volt mark. As the depletion region collapses, the line shows an abrupt exponential spike in current. This specific, highly nonlinear trajectory is described mathematically by the Shockley diode equation. Because this curve is an exact reflection of the material properties of the silicon, engineers can intentionally alter the fabrication process to drastically warp the shape of this curve for specialized tasks, for example, the Zener diode. By heavily increasing the atomic doping concentration during manufacturing, engineers intentionally narrow the depletion region. On the graph, this results in a sharp vertical drop occurring in the reverse bias quadrant. This narrowed region allows for a safe, non-destructive breakdown. The Zener diode can reliably conduct current backward at a highly specific voltage, making it perfect for stabilizing and regulating power supplies. In a Schottky diode, the P-type silicon is removed entirely and substituted with a solid metal contact. Looking at its curve, the forward bias spike occurs much earlier, typically around 0.3 volts instead of 0.7. Eliminating the P-type silicon eliminates minority carrier storage. Without those carriers lingering in the junction, the Schottky diode can switch states incredibly fast and operates with a significantly lower forward voltage drop. We can also swap silicon for materials like gallium arsenide, which possess a direct energy gap between the conduction and valence bands. In these materials, when an electron drops into a hole, it must shed its excess energy. Because of the direct alignment of these specific energy levels, that energy is released outward as a discrete burst of light, a photon. Whether they are regulating power grids, enabling high-speed computing, or generating light, all of these highly specialized functions stem from microscopic manipulations of the standard PN junction. Real-world electrical systems are highly dynamic. Voltages do not stay constant, they shift and reverse continually. This is a schematic for a half-wave rectifier. It is the most fundamental circuit application for a diode, used to manage those shifting voltages. The graph on the input side displays a standard alternating current sine wave. The voltage is constantly swinging from positive to negative, reversing polarity dozens of times a second. As the AC wave rises into its positive half cycle, that raw input hits the diode. This positive cycle perfectly triggers forward bias. The diode's internal depletion region collapses, allowing the voltage to pass through the component and to the output intact. But an instant later, the AC wave dips below zero, moving into the negative half cycle. The reversed polarity triggers reverse bias. The depletion region expands, entirely blocking the current from reaching the output. The final output graph reveals the result. The diode has simply clipped the alternating waveform in half, discarding the negative troughs. The alternating wave has been converted into a pulsing, single-direction direct current. This specific conversion from AC to DC is a strict prerequisite for modern electronics. Delicate logic boards and processors cannot survive alternating voltages. They require steady, unidirectional power to operate. A basic power supply contains multiple rectifiers working in tandem. Scaled up across modern infrastructure, billions of these nonlinear barriers operate simultaneously. The macroscopic control of our energy grids and global data networks relies entirely on our precise mastery of the microscopic depletion region.